Hello everyone. Today we are here to explore a property of the simple harmonic motion which we call the period. Our experiment aims to measure the time period of oscillation of an object under the restoring force of a spring. Although our primary goal is to measure the period, the experiment will also require us to validate Hooke's law, as you will shortly understand. Let's first take a look at the equipment we have. So we will use a 1 meter ruler, 20, 50, 100 grams of masses, a spring, and as you can see in the right side, we have a clamp and the tape to stabilize the spring while we are doing our calculations. So let's take a look at the period formula that forms the basis of our experiment. As you can see here, T represents the period. We have the numerical value 2 pi, and inside the root, we have the value m over k. Here, m represents the mass of the weights we will use, which are 50, 100, and 150 grams. So the only value that is unknown in this equation is k, which is the constant of our spring. We need to calculate it. So let's take a look at the Hooke's law and see how we calculate it. In this formula, F is the force that we apply, and we also have an x, which is the elongation of the spring caused by F. And we also have the constant k, as you can see. So to find k, we will use the weights of our masses. So we get the second equation here, which is mg equals kx. So since we are using the second equation, let's see how we will use it first. So in the first picture, we have a point of reference, as you can see. And in the second picture, I have the free elongation of the spring with no weight. In this slide, in the first picture, you can see the elongation for the mass 20 gram, and in the rest, you can see the elongation of the masses 50 and 100 grams respectively. So these were the measurements. And now let's take a look at the calculations I dried out of this. So here are the calculations, but I won't walk you through it. You can stop the video and take a look. However, I need to point out something before moving on. As you can see, there are some non-equal calculations at the bottom of the photo. As you can see, it's 6.54, 8.4, and 7.21. These are due to the possible errors that we will talk about later. However, to successfully accomplish the experiment, we will use the average of these values. So since there are no unknowns left in the period formula, now we can proceed. So let's watch the video of our experiment. As you've seen in the videos, we filmed the whole experiment process with my assistant. And then I used the slow motion analysis application to calculate the time it takes for the spring to return to its lowest point from the moment it's released. So this gives us the period. And then I subtracted the start and end times by the help of the application to find our experimental values. So here are the photos from the application. This is for the 50 gram. This is a period calculation. As you can see, the ending is 0.63 and the start point is 0. Here for 100 gram, the ending point of the time is 6.20 and the start is 5.32. So overall we get 0.88. And this is similar to the previous ones and 150 gram. Then we did our theoretical calculations, as you can see on the screen. You can stop whenever you want and take a look at that. Finally, I transferred a table for visualization and then to a graph, as you will see later. The purpose here was to calculate my error rate and observe how close the theoretical values are to the experimental values in the graph. Here in the screen, you can see the table. Okay, let's just investigate the table a bit. Here we have the columns: weight, theoretical period, experimental period, and difference period, and error rate. We have the weights 50 grams, 100 gram, and 150 gram, and the other values are put in the table from the previous calculations. And here is the graph. Please note that the red dots in the graph represent the theoretical calculations, while the blue ones represent the experimental calculations. So in conclusion, we have achieved an average error rate of 14%. The factors contributing to the error margin in this experiment are listed in the screen, as you can see. And I also want to point out that there can be many more possible errors contributing to the error. So in the end, we can say that our experiment was successful with a 14% error rate in average. In this experiment, we have learned how to find the constant k and successfully observed the period of the simple harmonic motion for the spring. Thank you for listening.